Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. If you found useful, please don't forget to like, share, comment and subscribe. Today we are going to discuss about the flow through an orifice, hydraulic coefficient of orifice, that is coefficient of velocity, coefficient of discharge and coefficient of contraction, and experimental determination of these hydraulic coefficients. Let me start the discussion on the definition of orifice. Orifice is a small opening through which the fluid runs full. So it is provided on the walls of the vessel or in the bottom of the container to transfer liquid from one place to another place. It is employed for the flow measurement and also for the flow control. So orifice is classified based on the size and shape. So based on the size of the orifice, we can classify the orifice as small orifice and large orifice. So orifice is also classified based on the shape, that is circular orifice and rectangular orifice. These are the most commonly recommended shape of the orifices. However, other shapes are also available, triangular orifice and square orifice. Another classification of orifice is based on the shape of upstream edge of opening of the orifice, based on which we can classify the orifice as sharp edged orifice. As you can see in this figure, the upstream edge of opening of this orifice is sharp edged. So this is the standard orifice which we are using for the flow measurement. Another type is round cornered or bell mouth orifice. The next classification of orifice, that is based on the discharge condition. Sometimes orifice is made to discharge freely to atmosphere. So it is called freely discharging orifice. Suppose we are discharging fluid from one vessel to another vessel and outlet edge of this orifice is completely under the liquid. Like this figure, you can see that the outlet portion of this orifice is getting submerged. So this type of orifice is called fully submerged orifice, whereas in this figure you can see that the water level at the outlet edge of the orifice is below the top edge of the orifice. So orifice here, it is known as partially drowned or partially submerged orifice. So discharge calculation for the different type of orifice are discussing in the subsequent sections. So next part we are going to discuss about Vena contracta of orifice. Consider a circular sharp edged orifice fitted to the side of the tank, and its orifice is made to discharge freely to atmosphere. It is a constant head tank. As the fluid approaches this orifice, the flow streamlines are getting converged. Then it becomes parallel. Then it is getting diverged. So because of the convergence of these streamlines, the shape of the liquid jet contracted to small area of cross section where these streamlines are parallel. So this point where streamlines are parallel with minimum area of cross section of the liquid jet, that is called Vena contracta. So from the Vena contracta, streamlines are diverged towards the downstream direction due to gravity. From the experimental observations, it is found that the approximate position of this Vena contracta from this orifice is at a distance of d by 2, where d is the diameter of this orifice. This tank is called a constant head tank. What is a constant head tank? So in this figure you can see that the liquid is flowing out through an orifice. Correspondingly, the same amount of water is entering into this tank, so that always a constant head of H is available above the center line of this orifice. At the Vena contracta, streamlines are parallel. So the pressure is uniform here, or it is equal to the pressure of the fluid surrounding it. So here you can see that the orifice is discharging freely to the atmosphere. So the pressure at this Vena contracta, that is equal to atmosphere pressure. Moreover, at this Vena contracta, the area of the cross section is minimum. So we have the maximum velocity. So consider a point 1 at the free surface of this tank and 2 at this Vena contracta. Now apply this Bernoulli's equation at this point 1 and 2. So P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus V2 square by 2g plus Z2. Consider the center line of this orifice, that is taken as datum, and Z1 is the distance from the center line of this orifice to the free surface, which is equal to h. Now the point 1 is at the free surface, so the pressure here is atmospheric pressure, and the velocity at this free surface v1, that is equal to 0. Correspondingly, here the orifice is discharged freely into atmosphere, so the pressure here equal to atmospheric pressure. So if you are substituting, then you will get v1 by rho g, that is 0, plus v1 square by 2g, that is also equal to 0, plus z1, that is equal to h, that is equal to p2 by rho g. So here also it is atmospheric pressure, so it is 0, plus v2 square by 2g plus 0. So if you are simplifying this expression, we will get v2 square by 2g equal to h, or v2 equal to root of 2gh. So v2 represents the velocity at the Vena contracta of the jet. This equation to calculate the velocity of the liquid jet at Vena contracta of this orifice is called Torricelli's equation, and this concept is known as Torricelli's theorem for flow through the orifice. So while deriving this Torricelli's equation, we haven't considered the losses. That means this expression for this velocity, that is represents ideal velocity. But for real fluids, we have to consider the loss of energy due to friction and surface tension. So if you are accounting the losses, then this actual velocity is less than this ideal velocity. So at the Vena contracta, area of the liquid jet is minimum and it is less than the area of the surface. So the discharge calculated is more than the actual discharge through the orifice. Hence, in real practice, we have to introduce some empirical constants called hydraulic coefficients to arrive actual velocity, actual area, and actual discharge. So these coefficients are called hydraulic coefficient of orifices, that is coefficient of velocity Cv, coefficient of contraction Cc, and coefficient of discharge Cd. In the next section, we are going to discuss how to determine this hydraulic coefficient of orifice experimentally. To start, we are going to discuss about coefficient of velocity, which is the ratio of actual velocity of the liquid jet at Vena contracta to the ideal velocity of the jet. Cv, that is equal to V divided by V theoretical, where V is the actual velocity, whereas V theoretical is the ideal velocity, which is calculated from Torricelli's equation. So Cv equal to V divided by root of 2gh. So the value of Cv, which varies from 0.95 to 0.99, depends upon the size and shape of the orifice and the head causing the flow. So how to determine the coefficient of velocity Cv experimentally? For which, consider a point P on this liquid jet. So the location of the point P is at a vertical distance of y and a horizontal distance x from the Vena contracta. Let V is the velocity of the liquid jet at Vena contracta, and the time taken by the fluid particle to reach this point P is t, or this horizontal distance x, that is equal to V into t. Now this vertical distance y, that is equal to half into gt square. Now this t is represented by x by v. By substituting t, that is equal to x by v, and expressing that in terms of v square, so y equal to half into g into t square, or v square equal to gx square by 2y, or velocity v, that is equal to root of gx square by 2y. So from Torricelli's equation, theoretical velocity, that is equal to root of 2gh. Now Cv, that is equal to the ratio of actual velocity to this theoretical velocity. So Cv, that is equal to V divided by V theoretical, that is equal to V divided by root of 2gh. So V is actual velocity, that is equal to root of gx square by 2y divided by root of 2gh. So the expression for Cv, that is equal to x divided by root of 4hy. During the experiment, h is available with us, and we can measure the value of x and y so that Cv can be calculated. In the next section, we have to discuss the experimental determination of coefficient of contraction Cc. The coefficient of contraction Cc is defined as area of the jet at the Vena contracta to the area of this orifice. So Cc, that is equal to AC divided by area. So AC means area of the liquid jet at Vena contracta. So how will you find out AC? AC can be determined by using micrometer contraction gauge. So you can see 4 micrometer screws. These 4 screws are adjusted till it touches the outer periphery of this liquid jet at Vena contracta. So mean distance of 2 pair of screws will give you the diameter of this liquid jet at Vena contracta. Correspondingly, we can calculate the area of the jet at Vena contracta and we can determine the value of Cc. So the value of Cc, which varies from 0.61 to 0.69, and it also depends upon the size and shape of the orifice. In the next section, we can discuss about the experimental determination of coefficient of discharge CD. So CD is the ratio of the actual discharge issued from an orifice to the theoretical discharge. So actual discharge Q, that is equal to area at Vena contracta into actual velocity of the jet. So area of the Vena contracta is equal to AC into actual velocity of the jet. So area of the jet at the Vena contracta, that means it is coefficient of contraction into area of the orifice. Actual velocity, that is equal to CV into root of 2gh. So the actual discharge Q, that is equal to Cc into A into Cv into root of 2gh. So theoretical discharge, that is equal to area of this orifice into theoretical velocity. So CD, that is equal to Q by QTH. So if you are substituting and simplifying, you will get CD, that is equal to Cc into Cv. So one way to determine CD is determine Cc and Cv experimentally and find the product of Cc and Cv. So that will give you directly CD. So the value of CD for an orifice which varies from 0.61 to 0.65, and it also depends upon the size and shape of the orifice. The actual discharge can also be determined by collecting this discharge in a measuring tank, or we can collect a certain volume of liquid in a specified time. So actual discharge can be determined, then CD equal to actual discharge divided by theoretical discharge. In the next section, we are going to discuss about the discharge through the orifice. Based on the size of the orifice, orifice can be classified into small orifice and large orifice. So for a small orifice, we can assume a uniform distribution of velocity of the section. So that means velocity, that is equal to root of 2gh, and discharge can be computed as Q equal to AV or Q equal to A into root of 2gh. Whereas for large orifice, we cannot assume the uniform distribution of velocity of the section. So what is a large orifice? For a large orifice, the head available above the orifice is less than 5 times the characteristic dimension of this orifice. So consider a large rectangular orifice. So it is a sharp edged rectangular orifice, and the top edge of the orifice is at a distance of h1 from the free surface, and bottom edge of the orifice is at a distance of h2 from the free surface. So this orifice is discharged freely to atmosphere. So consider a small element within this flow area. So this element is having thickness dh. So this is the orifice. Orifice has width b and depth d, and this element is at a distance of h from the free surface. So velocity of this fluid element, that is equal to v equal to root of 2gh, and the corresponding discharge dq, that is equal to area into velocity, or dq, that is equal to cd into dh into b represents area. So this is dh and this is b. So dh into b represents the area into root of 2gh. So this is the velocity. So total discharge that is passing through this orifice, that is equal to integral of dq between the limits h1 to h2. So q, that is equal to integral of dq between the limits h1 and h2. So if you are substituting for dq, it is integral between the limits h1 and h2 cd into dh into b into root of 2gh. So for a given orifice, cd and b, they are constants, and root 2g, that is also constant. So the only variable here is h, which is integrated between the limits h1 and h2. So if we are rewriting this expression, this equation can be written as cd into b into root 2g into integral of root h dh between the limits h1 to h2. So if you are integrating and substituting, you will get q equal to cd into b into root 2g into h raised to 3 by 2 by 3 by 2 between the limits h1 to h2, or it can be expanded as q equal to 2 by 3 cd into b into root of 2g into h2 raised to 3 by 2 minus h1 raised to 3 by 2, where h1 is the distance from the top edge of the orifice to the free surface. Similarly, h2, that is the distance from the bottom edge of the orifice to the free surface. Remember, this equation is the discharge equation for an orifice which is discharging freely to the atmosphere. In the next section, we can discuss the discharge equation for a fully submerged orifice. So here you can see two tanks, and this is the top edge of the orifice. So that means outlet of this orifice is in submerged condition. So it is called fully submerged orifice, or it is also called fully drowned orifice. So velocity of the flow through the orifice is getting affected by the level difference between these two tanks. So discharge here, that is equal to area into velocity. So what is the flow area? Flow area, that is equal to B into D. So D is the depth of this orifice and B is the width of the orifice, and velocity, that is equal to root of 2gh. So discharge equation for a fully submerged orifice, that is equal to area into velocity, or it is equal to q equal to cd into b into h2 minus h1 into root of 2gh. This is the area, that is b into h2 minus h1 into root of 2gh. h2 minus h1, that is equal to d, that is the depth of this orifice. So the discharge equation for a fully submerged orifice can be written as q equal to cd into b into d into root of 2gh. Suppose the outlet edge of the orifice is above the level of the water. Here you can see that this is the top edge of this orifice, which is above the water. So this orifice is partially under submerged condition. In this case, we have to divide the discharge into two. That is, the discharge through this portion, we have to treat the freely discharging orifice, whereas the discharge through this portion, we have to treat as the discharge through a submerged orifice. So the level difference between these two tanks, that is equal to h. So Q1 represents the discharge for an orifice discharging freely, whereas Q2 represents discharge for an submerged orifice, that is this portion. So in the first case, the head is varying from h to h1. So Q1, that is equal to 2 by 3 cd b root 2g into head is varying from h to h1. So it is h raised to 3 by 2 minus h1 raised to 3 by 2. Whereas in the submerged portion, the flow area, that is equal to b into h2 minus h. So this is the flow area from this portion to this portion. So flow area equal to b into h2 minus h. So Q2, that is the discharge for submerged orifice, that is equal to cd into, this is the flow area, b into h2 minus h into root of 2gh, because h is the level difference between these two tanks. So root of 2gh represents the velocity of the flow through this portion. Now the total discharge is the summation of discharge for an orifice discharging freely plus discharge for submerged orifice. So the total discharge Q equal to Q1 plus Q2. In the next section, we can discuss conceptual problems. Here you can see that a large tank which is provided with two identical orifices, and these two identical orifices are fitted in the same vertical line. Since these two orifices are identical, coefficient of velocity is same, that is given as 0.95. Now we have to determine the position of this intersecting point of these two jets. So the distance between these two orifices are given, that is equal to 2 meters, and the first orifice is at a distance of 2 meters from the free surface. Now h2 is the distance of the second orifice from the free surface, whereas h1 is the distance of the first orifice from the free surface. So vertical distance of this intersecting point from the first orifice, that is equal to y1, and the second orifice, that is equal to y2, and the horizontal distance from the Vena Contracta, that is represented by x. So we have to determine this y1, y2 and x. So the expression for CV, that is equal to x by root of 4hy, and the given data are h1, that is given 2 meter, h2, that is equal to h1 plus the distance between these two orifices, so that is 2 plus 2 equal to 4 meter. CV is given as 0.95. Since these two orifices are identical, its CV equal to same. So CV square, that is equal to x square by 4hy. So equating the value of CV for the first orifice and second orifice, we can write x square by 4h1y1 equal to x square by 4h2y2. So if we are substituting, then we can establish a relationship between y1 and y2 as y1 equal to 2y2. So in this problem, the distance between the orifices are given, that is equal to 2 meter. So from this figure, we can establish a relationship between y1 and y2 as y1, that is equal to y2 plus this distance. So from the figure, we can write y1 equal to y2 plus 2. So if you are solving this, we will get y2 equal to 2 meter and y1 equal to 4 meter. Now CV is given to us. So CV equal to x by root of 4hy. So how will you find out x? So CV square equal to x square by 4hy. So for the first orifice, we can write x square equal to CV square into 4 into h1 into y1. So h1 is given to us, that is 2 meter, and y1, that is also we determine, that is equal to 4 meter. So if you are substituting, then you will get x equal to 5.374 meter. So that is a horizontal distance of this intersecting point from the Vena Contracta. All of you can solve this problem by your own and verify the answers. The next problem we are going to discuss about the discharge through a fully submerged and partially submerged orifice. So here you can see a rectangular orifice of 0.5 meter wide and 0.8 meter deep is fitted to a vertical wall of a large tank. So the water level in this tank is 6 meter above the top of the orifice. So that means H1 equal to 6 meter. Find the discharge from the tank if the water level in the other side of the orifice is 1.5 meter above the top edge of the orifice. So in the first part of the problem, this orifice is submerged. So that means the top edge of the orifice is below the water. So this distance is given as 1.5 meter. And the dimension of the orifice is given, that is B equal to 0.5 meter and D is given as 0.8 meter. So H1 is also given to us. So H1 equal to 6 meter, whereas H2, that is equal to H1 plus D or H1 plus 0.8. So first of all, we can copy down all the given data. In the first part of the problem, water level in the side of this orifice is 1.5 meter above the top edge of the orifice. So that means now this orifice is under submerged condition. So discharge equal to CD into area into velocity. CD is given as 0.62. So Q can be calculated as CD into BD into root of 2GH. So BD represents area of the orifice and the root of 2GH represents the velocity. So H is the difference in water level between the upstream and downstream side of the orifice. It is given that the top edge of the orifice is at a distance of 1.5 meter from the free surface. So H equal to H1 minus 1.5. So that is equal to 4.5 meter. Now Q can be calculated as CD into area into velocity, that is equal to 2.33 meter cube per second. So the discharge through the orifice in the submerged condition, that is equal to 2.33 meter cube per second. So in the next part of the problem, so water level available is 0.3 meter below the top edge of the orifice. So that means now this orifice is in partially submerged condition. So that means this portion of the orifice is an orifice discharged freely to atmosphere and the bottom portion of this orifice is under submerged condition. So the total discharge equal to discharge for an orifice discharging freely Q1 plus discharge for submerged orifice Q2. First of all, we have to copy down all these data. Q1 that is discharge for an orifice discharging freely, head varies from H to H1. So H1 is available. So H equal to H1 plus this distance. So this distance that is equal to 0.3 meter. So H equal to 6 plus 0.3. For calculating Q1, head varies from H to H1. So Q1 equal to 2 by 3 CD B into root of 2G into H raised to 3 by 2 minus H1 raised to 3 by 2. And for submerged portion, that is Q2, the flow area that is equal to B into H2 minus H, because this is the flow area, that is B into H2 minus H. So Q2 equal to CD into area into velocity. So flow area equal to B into H2 minus H, that is B into H2 minus H, that is the flow area, into velocity of this flow depends upon this H. So H is the level difference between the water levels upstream and downstream of this orifice. So H equal to 6 plus 0.3, that is equal to 6.3 meter. So for the submerged portion, Q2 that is equal to CD into B into H2 minus H into root of 2GH, because the submerged portion is this portion. So that means area equal to B into H2 minus H. So Q that is equal to Q1 plus Q2. So Q1 represents discharge for an orifice discharging freely, that is this portion, whereas Q2 that is equal to discharge for submerged orifice, so that is flow through this submerged portion, equal to 2 by 3 CD into B into root of 2G into H raised to 3 by 2 minus H1 raised to 3 by 2 plus Q2 is CD into B into H2 minus H into root of 2GH. So total Q that is equal to Q1 plus Q2, that is equal to 2.745 meter cube per second. So all of you please solve this problem by your own and verify the answer. So these devices are commonly used in the field. So please try to differentiate the discharge calculation of an orifice which is discharging freely to atmosphere and a submerged orifice from a partially submerged orifice. Now this session comes to an end. For the time being it is enough. Thank you. Please don't forget to press the bell button to get the notification of next video.